Okay, guys, I want to get started because I've run out of time in this lesson. I ran out of time in the first class, and I want to make sure I don't this time. So let's got the worksheets that I handed you. Let's start right in Chapter 7, okay? Now, excuse me, Chapter 7 is really dealing with the same types of problems that we dealt with in Chapter 6. The only difference is now we're dealing with samples, okay? So when you see the word samples, you're going to be asked questions about the mean of the sampling distribution of X bar. What that is, every time you see X bar, you think sample mean. This is the mean of the sampling distribution of sample means is what they're asking about. We usually just call it X bar because there's just too many words in that title, right? So the mean of anything for us is not going to change. The mean of the sampling distribution of sample means is equal to the mean of the population. That's your formula. It's in your formula sheets. But what you need to know is whatever the mean is, that's going to be the mean. So for this one, they told us the population mean was 388. We can say the mean of the sampling distribution of X bar is also 388. Okay, it didn't change on us. So that's kind of a good thing. We don't have to worry about calculating the mean. We do, however, always have to worry about calculating the standard deviation. Now before, you were given, Chapter 6 problems, you were given the standard deviation of the population. You're given it again in these problems, but the standard deviation of the sampling distribution of sample means, in other words, the standard deviation of X bar, we have to take that standard deviation of the population and we have to divide it by the square root of the sample size. So what you have to do is you have to say 159 divided by whatever was the sample size in this one, what was 121. So I'm going to say 159 basically, right, divided by 11. Isn't that the square root of 121? It won't always be, it won't usually be that easy, to tell you the truth. So we'll do it like this. We'll say 159 divided by the square root of 121. It's going to give me 14.4545. And, you know, basically, go to 4 decimal places with these standard deviations. Sometimes in these problems it's nice to have more than that, but 4 should be sufficient, okay, for all the problems that you've been given. Standard deviations, no matter what it tells you to round to for the answer, for standard deviations, go to 4 decimal places at least, okay, or you won't get close enough to the problem answer. Okay, so that's our 2 things we really have to keep in mind. The mean is the mean. Whatever the population mean is, that's the sampling distribution mean too. The standard deviation, we've got to adjust it. We're going to take that population standard deviation, divide it by the square root of the sample size. Okay? How do you know that you've got this type problem and not the other type that we did in Chapter 6? Well, look, it gave us a sample size. It didn't give us a sample size in Chapter 6, did it? So this is one clue, okay? Can't always count on the clues to be 100%, but that's a good clue. Number 2, a population distribution is skewed to the right. It's skewed. It has a mean of 238. In other words, it has a population mean of 238 and a standard deviation of 36. So that's the population standard deviation. And then they say a sample of size 53 is drawn. Now I'm going to get used, I want you to get used to picking those 3 things out. Sorry, that should say mean. Picking those 3 things out, okay, of every problem that you get, or most of the problems are going to have it. And then it says, can the central limit theorem be applied? 2 things the central limit theorem demands. For you to be able to use the z-table to calculate these probabilities, that means that you have to have a normally distributed population or a sample size of at least, do you remember the number? 30. That's the central limit theorem. So you can have a skewed population as long as your sample size is 30 or more. You can have a sample size of 10 as long as you have a normally distributed population. Do you understand? You've got to have one or the other. You either got to have a normally distributed population or you're going to have a big enough sample size. That's the central limit theorem. So for the next question, it says that its normally distributed population tells you the mean and the standard deviation. It says a sample of 14. Well, that's not big enough if the data was skewed. But since the data was normally distributed in the first place, you're okay. This one's okay and that one's okay also. Yes, you can use the central limit can be applied, and we can use the z-table to calculate our probabilities. All right, so next we're going to consider a population. The size of that population is represented with a capital N. Please note that. That's not a sample size. That's a population size. It's 5,400. It says there's a mean, population mean of 180, and standard deviation of the population is 20. And we're going to compute the following z-values for sample distributions of x bar with the given sample size. So now it tells us a sample size of 104. In other words, n is equal to 104. Now, why do I care when I'm calculating z? Because remember the calculation for z. It's x, now it's going to be x bar, minus the mean divided by standard deviation. Used to be the population. Now it's the standard deviation of x bar, which I have to take the standard deviation of the population and adjust it every time. So I'm going to take my standard deviation and divide it by the square root of the sample size. And I come up with 1.9611. Now I can calculate z. The z value needs to be corresponding to x bar is equal to 178. Well, the formula is x bar minus the mean divided by the standard deviation of x bar. It's in your formula sheet. It doesn't change much from what we did in Chapter 6. We use the sample mean of 178. We use the population mean of 180. And this time we have to divide by this. We had to do that calculation first, okay, to get it. So I get a negative 1.0198, which I would make, negative 1.02, right? Because it's a z-score. We're going to round to 2 decimal places with that one. You can do the next one. 116 observations. So they changed the sample size. They changed the sample size. My standard deviation changed, didn't it? I got the same population standard deviation, this time divided by the square root of 116. So I have to do the calculation for that again, and I get 1.857. Okay, the rest of it's easy. I'm going to go, what are they interested in here? Well, sample mean of 174. They also changed that, didn't they? But the difference here is I'm really dividing by a different standard deviation, right? I'm getting a negative 3.23 here. Okay? Do you understand? So for Chapter 7 problems, you've got an additional element added. You got a sample size. You got to take that sample size and adjust your standard deviation. And then you basically do everything the same way as far as calculating z. You just use that new calculated standard deviation. If they change the sample size, you got to recalculate it, okay? You understand? All right, then page 2. Let's see what this one has for us. Page 2 says we got the weights of all Florida manatees is 25 pounds. That's the standard deviation, not the weight, is it? Standard deviation of the weights. Okay, so the standard deviation of the weights of all, then that population, that word all is really important. It means it's a population item. So you kind of want to circle it every time you see it. So I've got all Florida manatees have a standard deviation of 25 pounds. X bar is going to be the mean weight for a sample of a certain number. So they haven't told me what n is, have they? They want to know that. They're saying what sample size. In other words, what's n? What sample size do I need if I want to get a standard deviation of x bar equal to 10? So they're saying, I want standard deviation of x bar to be equal to 10. What does my n value equal? Well, n is equal to standard deviation divided by the standard deviation of x bar. And we take those numbers and we square it. It's in your formula sheet. I'm giving you the formula straight out of the formula sheet, okay? Just note, they're under Chapter 7, okay? There it is. And you'll have it on the test, of course. So all I have to do is go, okay, I want a 25, standard deviation of the population is 25. I'm going to divide that by what I want is 10, and then I have to square it. It's really 2.5, isn't it? 25 divided by 10 is 2.5. 2.5 squared is going to give me 6.25. Now here's my problem. I want you to note this, circle it, do whatever it takes to make you understand this statement right here, okay? Round the solution up to the next nearest whole number. They wouldn't have said round up unless they didn't want you to ever round down. Now, rounding means that we go to, where the closest one is, either to 6 or to 7, but not in this case of sample sizes. In sample sizes, we go to up to the next whole number, always, up to the next whole number. If that calculation had come out to be 6.01, you go up to the next whole number. Do you understand? Because we're taking samples of manatees. Well, nobody has ever been able to sample a fourth of a manatee before. How many do you have to sample? We got to sample at least a whole manatee, so I got to go up to 7. This is going to round up to 7. You understand that, right? So in other words, when you're talking sample size, never go down. Always go up. If it ends up on a whole number, well, you're great. But if it ends up on a 6.21 or 6.3 or something, that you would normally go down, you don't. You go up. Okay? Okay, next. The population distribution is normally distributed with the mean of 95, standard deviation of 21. This information is going to be used to get 2 probabilities. Round the solution 4 decimal places if needed. The probability that a single randomly selected observation is less than 90. Now look, guys, a single randomly selected observation is not a sample mean. This is a chapter 6 problem. You just finished all those, right? This is not chapter 7. This is to make sure, I wanted you to compare one side by side, okay? Chapter 6 compared to chapter 7. This is a single randomly selected observation is X, not X bar, right? So I've got the population mean. I've got the population standard deviation. I know how to draw my curve, don't I? This is X value. What's the mean? Well, what the mean always is 95. And they're saying randomly selected observation less than 90. In other words, the probability that X will be less than 90 is my question. That's my probability statement. Well, 90 would be right in here somewhere. And I can find that z-score and find that area. And that's the shaded area, so all I have to do is find it and look it up. Z gives me area to the left, so I'm good there, right? Okay, so I'm going to say Z is equal to 90 minus 95 divided by, now do I need to adjust the standard deviation? Nope, no sample size is involved in this question, right? So it's just use the population standard deviation, just like we did in chapter 6. So I really got a negative 5 divided by 21, don't I? And I get a negative 0.238, which I'm going to say is a negative 0.24. And then I go to my table and I look that up because that's easy. Z gives me area to the left, negative 0.24 is right in here somewhere, 0.4052. Okay? So this area is 0.4052. That's the answer to my probability question. If they asked me for percentages, I would change it to 40.52%, but don't just go randomly changing your answers to percentages. This is the correct answer for a probability question, is a decimal, right? Unless they ask you for the percentage. Okay, so that's the chapter 6 problem, just like you worked many of them by now probably. Now let's look at a probability that a sample of 62 randomly selected observations, all of a sudden, I have N. If I have N, I have a brand new standard deviation that I have to calculate. All of a sudden, I'm not dealing with X. I'm dealing with X bar, okay? Look at where I put it on the graph, okay? It's not an X, it's X bar. It's a sample mean, not a sample observation. So what's the mean? Well, the mean hasn't changed. That's always going to be the same. Okay?
90.
Isn't it 95?
No, it says find the probability of 62 less than 90.
that was the observation that we were going, less than 90.
Oh.
The mean is up here. Mean is still 95.
Oh, okay.
Okay? So I want to go still. They want to know the probability the random sample of observations has a mean less than 90. Well, sample mean less than 90. Looks the same, doesn't it? My graph looks exactly the same except for its x bar here instead of x. So how do I calculate it? Well, this time I've got to say, okay, probability that x bar is less than 90, because I'm dealing with sample means, and I need a standard deviation of x bar. Okay, I'll take the standard deviation, which was, what was it, 21, divided by the square root of my sample size, which is 62. I come out with, and go to 4 decimal places with them, 26670 is what I get. And then I'm going to have to use that to calculate z. I'm going to take that sample mean of 90, subtract the population mean of 95, divide by the newly calculated standard deviation. And I have negative 1.874. So that's going to be negative 1.87. And I look it up. Negative side of the table, 1.8, where is it, 7? I get 0.0307. Okay, perfect. That's the answer to my question. 0.0307 is the probability. Because it's an area to the left problem, I don't have to do anything. Z-table gives me area to the left. Are you good with that one so far? All right, now let's look at the next one. Distribution of the ages. I know I'm going fast, but I'm going to run out of time if I don't. You have a test next week, so understand this is on video. If you should work these problems, then you should check it and go back to the video, okay, if it gives you trouble. Okay, so I've got a distribution of all IRSC students. That would be population, right? Is normally distributed, a mean of 21.3 and a standard deviation of 5.8. They're talking about population. So this is the population mean, and this is the population standard deviation. And then it says, use this to do this. Find the probability that a random sample of 63, so they gave me a sample size. And as soon as they give me a sample size, so that I don't forget to do it, I go ahead and calculate the standard deviation of the sampling distribution of sample means, okay? I'm going to say standard deviation of x bar is equal to that standard deviation of the population divided by the square root of the sample size. And I'm going to get 0.7307. All right, let's find the probability that this group of 63 students, one of our groups, has a mean age between these two numbers. Well, those are x bars that we're interested in, aren't they? I want the probability x bar is going to be between 18.9 and 21.5. Got it? So here's z, here's 0, here's x bar, and the mean is the mean, right? So I got 90, what was it? Not 90 something, 21.3. Better. So let's place our two scores that we're interested in. One's on one side and one's on the other. Now it doesn't have to be that way, it just so happens to be that way for this problem. So when you have an area between two z-scores, you're going to have to look them both up and subtract the smaller one from the larger one. There's really no other way to do it, right? I'm kind of slowing down because I'm hoping that you're working ahead of me, because then you can get the most benefit out of what I'm doing here, okay? All right, so I know I have to calculate the standard deviation. I did it. I know I've got two z-scores. So the first one, I take that X bar I'm interested in, I subtract the mean, and I divide it by my calculated standard deviation. This is where everybody goes wrong. They forget what they're doing. This is a sample problem, right? Sample mean problem. We've got to adjust the standard deviation. And when I do that, I came up with negative 3.28. This one is a negative 3.28. Next one. I know another z-score, z2. That one's equal to 21.5 minus 21.3 divided by 0.7307, and that is equal to a positive 0.27. That's my new z, my other z. Now look, I just want to point something out because this happens to a lot of students, and a lot of students make this mistake. They get used to working over here and saying, well, this I'm going to subtract, I'm going to go this one, the first one I come to, minus the second one, the middle one. And then when they have one that's higher than the mean, they go mean minus x bar. And it's never mean minus x bar. It's always x bar minus mean. Understand, this thing right here in the center is always the one that you subtract. The one you subtract from is your sample mean, the one you're interested in. Just keep it in mind because it's an easy mistake to make. Now I've got a negative 3.28. I'll go over here real quick. Negative 3.28, I get 0.0005. That's that area. And I've got 0.27, got to go to the other side of the table for that one. 0.27 is 0.6064. And I'll subtract 0.6064 minus 0.0005. I'm going to end up with let's see, I've already done it, 6059. Okay, that's my answer, 0.6059. If they asked for it as a percentage, I would say it's 60.59%. Are we good so far? Yes? So far we haven't hit anything too unusual, have we? All right, let's go on. Okay, so Goliath groupers, which evidently weigh quite a bit, caught on the Treasure Coast, their average weight is 403 pounds. It said all, so that's going to be my population, right? My population mean is 403. Okay, they have a standard deviation of 58. Since it's talking about the population in the sentence and it hadn't changed anything, it's got to be the population standard deviation. And then they told me this, there's going to be a sample taken of 62. Next step, go ahead and calculate that standard deviation because you're almost guaranteed you're going to need it, right? In other words, I'm taking sample distribution, so I'm going to say standard deviation of x bar is going to equal that 58. 58, that's a 5, divided by the square root of 62. And I'm going to get 7.3660. Okay? It's going to be my standard deviation that I'm going to use. If they ask about sample means, that's what I'll use. Now, the probability the average weight of a sample of 62 is within 9 pounds. They want within 9 pounds of the average weight of all. The average weight of all is the population mean, right? So let's draw it. We're dealing with sample mean, so we got to put x bar down here. But the average weight of all is the mean, which goes in the middle. Now, they said within 9 pounds. Guys, that's plus or minus 9 pounds, okay? So I'm going to go over here, and I'm going to say 403 minus 9, right? It's going to give me 394. And 403 plus 9, well, that's going to give me 412. They want to know between those two numbers. It's another between the two z-scores problem, right? So the probability statement is the probability that x bar is between 394 and 412. Now, read the problem again and see if we got it right. After you set it up, you should always do that. They want the probability that the average weight of a sample of 62 is within 9 pounds of the average weight of all. Average weight of all is 403. Within 9 pounds is plus or minus 9. So I say it's between 394 and 412. All I did was add and subtract 9, right? Okay. Now this next thing I got to know is, okay, I already calculated my standard deviation up here because I had a feeling I was going to need it. And now I need z-scores, don't I? The first one is going to deal with that sample mean of 394 minus the population mean of 403 divided by, oh, good thing I calculated it, 7.3660. And that score is going to be a negative 1.22. Now, you calculate the other one the same way, but look at this table and tell me, do you know what the other score is already?
Yeah, it should be positive.
It should be. It should be the exact same thing, just positive. Why? Because it's the exact same distance from the mean, right? We set that up deliberately. We said minus 9, plus 9. These scores have to be mirror images of each other. But if you want to do the calculation, or you just don't think about that, go ahead and do it. It's 412 minus 403 divided by 7.3660, and that's going to give you that positive 1.22. Now, it doesn't help us as far as looking up the data because these numbers are different enough. They're asking us different things. We have to take the tail of this one, and we have to take the entire left side of that one. So it won't help us there, but it does help us to recognize that those are mirror images of each other. I've got a negative 1.22. I get 0.1112, okay? I go to positive 1.22, and I get 0.8888. Did I say 8's enough? 0.8888. So I take that 0.8888, and I subtract that 0.1112, and I come up with 0.7776. That's my answer. Okay? Next question. There's a weather service that says the mean daily temperature in Jensen Beach is 72.4. Now, it didn't say sample anything, did it? So it's probably talking population. I'm going to say the population mean is equal to 72.4. And it has a standard deviation of 4.3. Population standard deviation, 4.3. And then it wants to consider the mean daily temperature in Jensen for a sample of 61 randomly selected days. Sample size is 61, right? So what's next? What would you do next?
Divide the standard deviation over x bar.
Divide it by, you're going to take that standard deviation, divide it by the square root of the sample size. You're going to calculate the standard deviation of x bar. I'm going to take 4.3, divide it by the square root of 61, because I know I'm going to have to use it. I know I'm going to have to use it when I calculate z for this problem, okay? Okay, next. They want the probability that the mean daily temperature of a sample of 61 randomly selected days is, here's what we want, greater than the mean daily temperature by at least 1.5. Well, okay. Here's my curve. I'm dealing with sample means, but still 72.4 is the mean of both, isn't it? And they want to know greater than this one by 1.5. Well, what are you going to do?
Do it on both sides.
They didn't say within. They said just greater than, didn't they? So I said, I got to find this number, don't I? And it would be 72.4 plus 1.5 is going to tell me where the cutoff is. I'm going to say 73.9. That's the number, and this is the area that's greater than that number, right? So they said at least 1.5. That's the probability that X bar is going to be greater than or equal to 73.9, right? Now, the equal to part doesn't change our probability one little bit. You left it off, it wouldn't matter, right? But you might have to pick the right statement on the test, and that equal would be important because it said is greater than by at least. This one would hit the at least. It would be 73.9 or greater. Now look, this is an area to the right problem. I'm going to calculate my z-score. I've already calculated my standard deviation up here. I'm going to calculate my z-score, same as always. I'm going to say 73.9 minus 72.4 and divide by the standard deviation of 0.5506. And I'm going to find out what that cutoff is. 2.72 is what I get. Okay, so how do I find the area to the right? Well, Z doesn't give you the area to the right, remember, it gives you the area to the left. You can find the area to the left, which is right here. We can look it up. We would look up a positive 2.72, wouldn't we? Whoops, sorry, 2.72. And it would be 0.9967. Okay, that entire area is 0.9967. That was not what they asked for, though. They want this area. So I could say, well, that's the rest of the curve, 1 minus 0.9967. And I would get 0.0033. There's the shortcut that makes it so much sense, though, since I recognize that this side of the curve is a mirror image of that side, that if I know that this area is 0.0033, then I know that the tail of a negative, the other side of the left side of a negative 2.72 is also going to be 0.0033. I can look it up on the negative side. So what do I look up? Well, I look up the negative 2.72, and look what I get. That's it, 0.0033. Don't have to subtract it from 1 if I remember that these match each side, mirror images, right? So I want, if you ever want the area to the right, if you ever want the area to the right, if you have a positive z-score, look it up on the negative side. If you have a negative z-score, look it up on the positive side, okay? Just look it up on the opposite side. It'll give you area to the right. Otherwise, Z only gives us area to the left, okay? It's just a shortcut. All right, so that's the area, and that is the actual answer to our question. The probability is 0.0033. That would not be 33%. That would be 0.33%, right? It's a very tiny probability there. All right, now let's look at a research poll that 79% of Americans say that, okay, I want to draw a line right here because we're changing gears. And these problems that we're going to talk about are going to be proportion problems. Now, you haven't hit proportion problems in Chapter 6, but you're going to get proportion problems in Chapter 7, and you're going to need to recognize what they are. Here's what you look for. First, the data is given to you in percentages. So when it talks to you about the percent of Americans, 79%, okay, the first thing that should go through your mind is this is probably a proportion problem. The second thing, look at the sample size in this problem. 300 Americans sampled. Proportion problems usually have larger sample sizes. Just saying, okay? I mean, we've been dealing with 14 or 62 or, you know, hovering around 30, but not with proportion problems. We got bigger sample sizes. That's another clue. The third thing, there is no standard deviation of the population given to you. We do that by calculation. So if you don't have a standard deviation of the population, you probably got a proportion problem. Now listen, I will get a bunch of emails this week. I'm waiting for them. I have a standard answer I always give. The email will say, I can't answer the question that they're asking me because they did not give me enough information. They didn't give me a standard deviation. How am I supposed to calculate the standard deviation of the proportion? Well, with a proportion problem, you don't have a standard deviation, okay? So watch what we do for proportion problems that make them different in our calculations, okay? 79% of Americans say U.S. economic system unfairly favors the powerful. That is a proportion. We write it as a decimal. This is called P. It's called the population proportion. It doesn't say all Americans here, but wouldn't you say 79% of Americans is understood that it means all Americans? So that's our population proportion. You can call it P. There was a sample of 300. And out of that sample of 300, 235 agreed that this system unfairly favored the powerful. So the question is, what's P? Well, P is how many out of the whole population fit the criteria. So P is equal to 0.79. And P hat is how many out of the sample fit the criteria. Well, there were 235. That's not my answer, though, is it? 235 out of how many? Well, the sample was a sample of 300. So in a sample of 300, 235 fit the criteria. Do you understand? Well, you're capable of doing that math yourself. Sorry, that should be a 3. You're capable of doing that math yourself. 235 divided by 300, you're going to get a decimal. The sample proportion is 0.78. The population proportion is 0.79. That's P and P hat. Okay? You see the difference? They took a sample, and you might not have the actual decimals given to you. You might have how many out of the population fit the criteria. Well, you can figure that out. You take the you have to have the population size, but you can figure that out, okay? Next, let's take question number 10. We have, I hope I've got this question here. Hang on a minute. Yeah. We have 46% of the voters in Martin County support a proposed new fire district. We're going to consider the sampling distribution of the sample proportion. Well, back to sample proportions. That's the only kind of proportion problems you've dealt with, so you're good with that. And there's a sample size of 217, and we want to get the mean and the standard deviation of the sampling distribution of P hat to 4 decimal places. Well, look, P is the population proportion. It says 46% of voters in Martin County. That's P. Okay? And then it says the sampling distribution of the sample proportion, sample size is 217. It gave us N. Okay, so let's see if we can answer the questions. That's all it really gave us, right? This is why I get emails about not giving me enough information. Okay, what's the mean? Well, the mean of the sampling distribution of the sample proportion, the mean of P hat, is equal to the population proportion. It's the mean is the mean is the mean, okay? Whatever the population mean, and we treat the population proportion just like we treat the mean, so that's the population mean for all practical purposes, okay? It's P. That's good. We don't have to do any calculations for mean. What about this one? Standard deviation of P hat is the one, go to your formula sheet, it's P times Q divided by N. Okay, we know P and we know N. Somebody tell me what's Q? P. Good, you got it. Q is 1 minus P, okay? Q is 1 minus P. So if this is 0.46, this is 0.54, right? P plus Q have to equal the number 1. If that's part of the data, then the rest of the data is in Q, okay? So this is easy. Square root of 0.46 times 0.54 divided by sample size of 217. Okay, this is not hard. It's just, it might be cumbersome as far as your calculator goes. You may have to use parentheses to make sure all of that stays under the radical. For mine, I just go 0.46 times 0.54 divided by 217, and it needs to all be under the radical. And some of you are going to have to close that parentheses off, okay? and I get 0.0338. Now listen, I always find trouble because there's so many decimals in proportion problems that sometimes I have told students to go to 6 decimal places with the standard deviation of the proportion, or 8 even. But I think all of your problems are working fine with just 4. So let's keep rounding standard deviations to 4 decimal places. If you find you're not getting close enough to the answer, take your standard deviation out further, okay? Because that's where, there's so many decimals in these problems, right? That the precision gets to be a crucial point. Okay, but that's how you calculate standard deviation, the mean, and the standard deviation of the population, the sampling proportion, right? P hat. All right, let's look at 36% of the observations possess a certain characteristic in this population. Well, that's going to be P, isn't it? Because it's talking about the whole population. And we don't care what the characteristic is. Maybe it's that people that had red hair or something. And then we're going to consider the sampling distribution with a sample size of 377. And this is what I always write down. I always write down P, I always write down N, and I write down Q because I know I got to have it. So you might as well write those 3 things down right off the bat, okay? If I have P of 30.36, what is Q? 0.64 is it. Okay? If you have doubts, subtract it from 1, right? Okay, so I've got P, Q, N, and now I want to determine the probability that in a random sample of 377, they haven't changed the sample size, always check that because sometimes they will, greater than 41% possess the desired characteristic, draw the curve. This time, you're dealing with P hat, sample proportions, okay? What's the center of that? It's always going to be the population proportion, just like it was always the population mean, right? And then they want to know greater than 41%. Well, greater than P hat, what the question is, probability that P hat is greater than 0.41. We don't write problems that we're working proportions in percentages. We change them to decimals. Okay, so here I am, 0.41. Area to the right, isn't it? Greater than 0.41. Okay, so now I don't have a standard deviation, but I got to have one. So I'm going to go standard deviation of P hat is equal to the square root of 0.36 times 0.64 divided by 377. And that's my calculation. What did I get when I did that one? 0.0247. I know I'm giving you all this, and you're not having to do any math, but it's because I want you to be able to go back to these problems later, and we got a lot to cover. Okay, how do I calculate Z? Well, that's going to equal this sample proportion of 41, the one I'm interested in, minus the middle one. And it's always that way. We always subtract the one in the center, right? And I divide by 0.0247. That's the standard deviation that I need. And I come up with a Z-score. My Z-score looks like 2.02. Okay. Area to the right. Well, I can look it up, and it would give me the area to the left, and then subtract that area from 1, or I can look it up on the opposite side of the table. This is a positive 2.02, but I'm going to look up a negative 2.02 and find that area. It's 0.0217. If that doesn't make sense to you, then go back and do the other way. But you should by now understand how the Z-table works. This is a mirror image of that side. So the tail end of this over here, which would be a negative 2.02, will equal that area. So this is my probability, 0.0217. Okay? Okay, so next they said, talking to the same problem, so they're going to change something on me. The thing you really have to watch for, guys, is this. Watch and make sure they haven't changed the sample size. Because if they change the sample size, you got to recalculate the standard deviation, okay? All right. This time they didn't, though. Sample size of 377, sample size of 377. I can use the same standard deviation. But this time it's between these two p hats. So they want to know the probability that p hat is between two numbers, and those numbers are 0.28 and 0.34. Okay? So I'm drawing it. I'm putting p hat down here, and I haven't changed the population proportion on me. It's the same data. But I'm going to go between 0.28 and 0.34. They're both over here on the left. I don't know where they go, but I'm just having to leave myself room to write, okay? And it's this area. Once again, area between two z-scores. I have to look them both up and subtract, won't I? So I'm going to work this really quick. I'm going to use that same standard deviation because I've got the same sample size. I'm going to take 0.28, subtract 0.36, divide by 0.0247, which gives me a negative 3.24. That's the first one. I'll call it Z1. Z2, 0.34 minus 0.36 divided by the same thing. The only thing I changed was the sample proportion I'm interested in. And this time I got a negative 0.81. When I look these up, negative 3.24 is 0.0006. Negative 0.81 is 0.2090, right? I got 0.2090. The only way to do this is subtract the bigger one minus the smaller one. And you get an area 0.2084. And that's your answer. That's the area between two z-scores. It's not really too much of a shortcut for doing that one, okay? Okay, moving right along. I know I'm going quick, but you do have a tape. Okay, so there's a Gallup poll. In this poll, 59% of Americans report they're better off financially today than they were a year ago. Okay, that looks like all Americans to me, so that's going to be P, right? And p hat's going to be the proportion in a random sample of 364 that say they are better off financially today than they were a year ago. Well, they match. It matches what the p-value was that they gave us. We have to kind of watch that. So we want the probabilities rounded to 4 decimal places that in that random sample of 364, less than 66% say they're better off. Okay, I'm going to go ahead and write this. Probability that p hat is less than 0.66. I'm going to go ahead and draw my curve because I'm thinking about it and I've been reading the problem. And this is the population proportion here, right? And where's my 66? Would be over here somewhere. Less than would be here. I don't know Z. When I get this area, it's an area to the left problem. I'll simply look it up. But now I have to calculate a standard deviation. To do that, I got to have P, Q, and N. Well, they gave me P, they gave me N. Q is what? 0.41, good. So my standard deviation, maybe I can put it right here. My standard deviation of P hat is equal to the square root of 0.59 times 0.41 divided by 364. All of that's under the radical. And I came up with 0.0258. Okay? Okay. Now, Z is going to be that interesting p hat minus the mean, or the center population proportion, divided by that calculated standard deviation. I think I did this, but I made a mistake in this last problem one time when I was working it, so I'm going to do it again, okay? I'm going to say 0.66 minus 0.59 and hit enter. I'm going to divide by 0.0258, and I'm going to get 2.71. Did I do that right? Is anybody
Yeah, no,
with?
you did it right.
Okay, good. Okay. So I got 2.71. Now all I have to do is look up 2.71. Where does it go? Positive side, right? 2.7 is here, 1 is here. I end up with 0.9966, okay? Is that right? Is that what I got? Let me make sure. Yep, looks like it's right. Okay? That's the probability that they will be less than 0.66. Okay, we like area to the left because all we have to do is look it up. All right, let's do another one. This says the Census Bureau says that 33% of Floridians have earned a bachelor's degree. We could assume that's all Floridians, so we'll say that's P. P hat's going to be the proportion who have earned a degree in a random sample of 386. Well, there's my sample size. So automatically I'm looking at this and I'm going, okay, I'm going to go ahead and do what I need to do. I'm going to say, what's Q? If P is 0.33, what's Q, guys?
0.67.
It is. And if that's the case, don't you think I should go ahead and make this calculation so that I remember what to do? I'll do the square root of 0.33 times 0.67. I'll divide it by 386. And I'll get that standard deviation of P hat. What did I get? I got 0.0239. Okay, I think I've got all the pieces I need, right? Now let's see what the question is. Find the probability that in that same random sample, they haven't changed the sample number on me. You always check that, okay? Less than 40.2% have earned a college degree. Okay, probability that P hat is less than, now look, this written as a decimal always looks strange to people, but you don't put 40.2, you put 0.402. Don't forget, you got to change percentages to decimals, okay? So now I've got Z, and I got P hat, and I'm going to put the mean or the population proportion in the center. I'm going to say, where would that 0.402 go? Well, it has to go here, doesn't it? And my question is about less than that, so that's this part of the curve. Good, it's another area to the left problem. As soon as I find Z, all I have to do is look it up. So I'm going to go Z is equal to 0.402 minus 0.33 divided by, what is it, 0.0239. Okay, 0.0239, I got 3.01. So I can look that up easily, and that gives me my answer. Positive side of the table, 3.01 looks like 0.9987. And now they're going to change it around a little bit and ask us some other questions, okay? They're going to say find the probability in a random sample of 386. Sample size still matches, so my standard deviation holds. I can still have that. Then it's between these two scores have earned a bachelor's degree. Now we've done a bunch of these. I'm going to set it up for you and tell you the answer, and I'm not going to work the rest of it because of time. I want the time on the last page, okay? But I'm this time, the probability that P hat is between, what were the numbers? 0.26, 0.266 and 0.296. That may be the hardest part. It's all over here. and I want the area between. Same standard deviation, Z1, 0.266 minus 0.33 divided by that standard deviation, 0.0239. Okay? Negative 2.68. Whoops, I'm sorry. Z2, 0.296, sorry, minus 0.33 divided by the same standard deviation. And this time I get a negative 1.42. They're both negative, but that's the way it matches to what I drew, doesn't it? Because when I look up negative 2.68, I'm just going to tell you it's 0.0037. When I look up negative 1.42, it's 0.0778. I take the bigger one, I subtract the smaller one, and I get the area between. And that's my answer, 0.0741. That doesn't change much. Area between two z-scores, you've got to look them both up, and you should be fine with that. Okay, now let's answer a couple of questions that are more understanding the problems that you're working on this last page. But first we have to work them the exact same way before we can answer the conceptual questions, okay? So first it says there's a New York State Board of Law Examiners says that approximately 69% of people taking the bar exam pass the exam. Okay, so that's going to give me my population proportion, because it's talking about all of the ones that took it, right? And then it says if 16 people have taken it, they're randomly selected, what's the probability at least 76% have passed? Well, I know I've got a sample size of 16 here, don't I? I need Q so that I can calculate my standard deviation. If P is 0.61, Q is 0.31. And then I can go over here and say standard deviation of the population proportion, of the sample proportion rather, is the square root of 0.69 times 0.31 divided by that sample size of 16. It's such a small sample size for a proportion problem, it's just weird. But anyway. Okay, it comes out to be 0.1156. All right. So 16 people have taken it, randomly selected. What's the probability? At least 76% have passed. I would write my statement as being probability that p hat is greater than or equal to 0.76, right? We'll draw it and say this is my population proportion here, and 0.76 would be over here somewhere. I don't know Z, but that's the area I want. It's an area to the right problem. In other words, for the shortcut, I'll look it up on the opposite side of the table, the negative side. But I have to find out what that Z-score is. Z is going to equal the 0.76 minus the 0.69 divided by my calculated standard deviation, 0.1156. And I get 0.61. Now, if I look up a positive 0.61, it's going to give me all of this. But if I look up a negative 0.61, it's going to give me the opposite, which is what I want. A negative 0.61 is 0.2709. Do it either way you want. Just make sure you're getting that answer, okay? That's my answer, 0.2709. Now it changes the sample size. It says if 40 people who have taken the bar exam are selected, what's the probability at least 76% have passed? Now, it didn't change the probability. It's saying, what's the probability that p hat is greater than or equal to 0.76, right? That didn't change. What changed is the standard deviation, right?
Yeah.
All right, we got to calculate the thing again. because they gave us a different sample size. So this time I'm going to go, well, standard deviation of p hat is equal to the square root of p, 0.69, times q, 0.31, divided by 40. And that's going to be a different number. This time it's 0.0731, isn't it? All right, so that's what I have to use. Now I'm going to go down here and draw it. I'm going to say this is z, and this is p hat, and this is 0.69. None of that changed. 76%, still the number I'm interested in. Still the greater than, right? Still the area to the right. Nothing's changed. My curve looks exactly the same. But z is now equal to 0.76 minus 0.69 divided by a totally different standard deviation. The standard deviation is decidedly what? Smaller, isn't it? Yeah. So we're going to end up with a score, this time of 0.96. Now that's really, like, you know, you can't tell in the pictures that you draw, but really that's further over, isn't it? In other words, this tail area is smaller, isn't it? So I'm going to have a smaller area here. When I look up a negative 0.96, because I'm taking the shortcut here, I come up with a 0.1685. Okay. Now, they're asking us a question. Why did that probability decrease from a 0.2709 to a 0.1685? It went down. Why would it go down? Sample change, which changed the standard deviation. Now look what happened to your standard deviation. It went from a 0.1156 to a 0.0731. It went down. Standard deviation goes down, doesn't it? It decreases the area in the tail of our curve. Everything gets compressed, okay? We have a narrower distribution. Everything narrowed in, we have a smaller area in the tail. Does that make sense? It's kind of hard to envision, but that's the answer to that, okay? Your standard deviation goes smaller, your probability is also going to get smaller if everything else remains the same, okay? All right, let's look at this one. 41% of Americans have less than $3.25 in the bank for an emergency. P hat's the proportion who have less than $3.25 in the bank for an emergency in a random sample of 75. By now you know the drill. P is 0.41, N is 75, and let's go ahead and say Q. Q is what? You got it, 0.59, right? So we're going to go ahead and calculate, because we know we have to, standard deviation of p hat. It's going to equal the square root of 0.41 times 0.59 divided by 75. All of that is going to give me a standard deviation of 0.0568. Good enough. Let's see what they're asking now. The probability, the proportion of people in a random sample of 75, haven't changed the sample size, good, who have less than 325, so that's what they told me about, that matches the population proportion, is within 9%. It's within 9% of the population proportion. Well, okay. Z, p hat, right? 0. What's the population proportion? 0.41. What two numbers do I need to be within? 9%. Yeah, so I'll take 0.41 and say minus 9%, which is a 0.09, isn't it? And I get 0.32. I was trying to find it on my list, my notes. That's 0.32. And I'll take 0.41 and I'll add 9%, which is going to be easy, right? 0.5. 0.50, since I've got everything in two decimal places here. I don't know Z, but I do have an area between two Z-scores, and that's easy to calculate. Let me write the probability statement. The probability that P hat is between two numbers, 0.32 and 0.50. That's what I'm interested in. I have two z-scores to calculate, but now it's a piece of cake, right? You've done this before. We've already calculated our standard deviation. I'll come over here and say z1 is equal to 0.32 minus 0.41 divided by, what's that standard deviation? 0.0568. There you go. And I get a negative 1.58. And I'll say z2. That's going to be this other one, 0.5 minus 0.41 divided by 0.0568. Same thing, right? And I get a 1.58. Well, okay, if I had been thinking, I wouldn't have had to do that calculation, right? I mean, they're both within certain numbers. They're equal distance from the mean. I do have to look them both up. There's no shortcut for that. Negative 1.58 is 0.0571. Okay. 1.58. Go to the other side. 9429. Subtract it. And I got 0.8858. I think I got that right. That's my probability that it's going to be between those two. In other words, it's going to be within 9% of the population proportion. Okay, so next question. Want the probability of the proportion of people in a random sample of 75. Guys, first check and see if they changed the sample size on you. Same sample size? Good. We're good then. Who have less than 325 in the bank, so it's the same population that they're talking about, is less than the population proportion by 15% or more. Okay. Here's what they're asking. This is just, you can always go ahead and put this down, right? That's just my data. Okay, that's my population data there. And they're saying, is less than this number by 15% or more. Well, 0.41 minus 15%, 0.15, right? I'm going to have 0.26. Okay, so this number I'm interested in is 0.26. And I'm interested in less than or equal to it, right? So I'm going to write my statement. Probability that P hat is less than or equal to 0.26, and then I just have to calculate Z. Well, here's Z. 0.26 minus 0.41. I didn't need to recalculate the standard deviation because they did not change the sample size on me. And I'll get a negative 2.64. With that negative 2.64, all I have to do is look it up. It's an area to the left problem. Negative 2.64, 0.0041. That's it. That's my answer. If they want that in a percentage, don't get confused. It's 0.41%, which is hard for us to write. It's a very small percentage, isn't it? So don't get confused when you're having to change, if you have to change things to percentages. Okay, I feel like I've talked really fast, but I did manage to get through it. I do want to note to you that this piece of paper that I'm showing you right now is a piece of scrap paper that I do give you on the test, okay? Because I know how hard it is to draw these curves and you get bogged down in it, so I will have paper like this for you to draw curves. Please label these curves, watch the videos again if you need to, make sure you're labeling them like I'm labeling them. I haven't decided if I'm going to do extra credit for perfectly labeling curves or not. If I do, everything has to match everything has to be exact. I would not give partial credit. So you're going to want to watch what you do. I do know that people who draw and label these curves correctly score significantly higher on these tests, this test and the final exam, okay? So it's worth it for you to pay attention to that and start working at it. All right, you've been great. Thanks for coming today. I will see you next week.